First and foremost, to all of our viewers and listeners, hello, and thank you for tuning in. With us today, we have speaking Nick Roe, Senior Network Engineer with Matrix Technologies. Nick has recently written an article on industrial networking for Control Engineering Magazine, and today he's going to be talking us through some of the material he covered in that article. So hello, Nick, and thank you for joining us. And just to get us started, if you could begin by providing our viewers with a brief overview of what industrial networking is and why it's crucial in today's manufacturing landscape.
Sure. Industrial networking refers to the interconnected infrastructure of devices and systems in order for a seamless data communication, as well as controls in an industrial environment, whether that's a manufacturing floor or, could be manufacturing or oil, anything that could be out in that uses faster data flow. While industrial networks share some similarities with traditional networks, industrial networks have their own communication protocols, which are unique to the processes and equipment that's involved, and also are more sensitive to the timing and latency of those communications. A reliable industrial network is critical for the process to occur in a sub-second latency. Industrial networks is also essential for driving the efficiency and productivity of manufacturing facilities. It allows for real-time monitoring, controlling of equipment, predictive maintenance, and it's also very consistent with the performance and quality of that end product. A well-designed and consistent industrial network enables distributed control systems to work for anybody involved, whether that's your thin client operators, traditionally called HMIs, also for the collection of historical data on any of those endpoints, as well as reporting that maybe management would like to see. How well is this line performing? Are we getting things out in a good sense of time? As well as learning the preventative maintenance, being able to track in real time, when we need to replace a part or when something is going to just need replaced. The whole, broader side of the industrial networking is, if you think of a house, you really want a good foundation of that house so everything can be placed upon it. Anybody that's went through the house design project, there's more than just cement and wood. You've got cabinets, you've got plumbing, you've got electrical, all those components. So network is a lot like that. An industrial network provides a backbone to which everything is going to communicate and rely upon. Whether that's your PLCs talking to each other, any servers or infrastructure that provides support to those pieces of equipment, whether it's operator workstations, PLCs, drives, robots, lines. Without a network, it's kind of hard to get that communication out there, and a reliable network at that.
I see. So you mentioned the word backbone, and I think you used that in your article as well. Maybe you've already answered this, but if you have any more information to share on the topic, could you elaborate a little more on why it is that having that reliable industrial network is so essential for various manufacturing processes?
You're right. So like the house, the network backbone, it's more than just physical media, whether that's copper or fiber that's ran around the plant that connects endpoint devices. It's the foundation. It's the main reliable source that the manufacturing process is going to rely on. That device, like I mentioned, controls PLCs to HMIs. It controls the motors and drives that the equipment uses to work on, as well as really any type of the data collection. So there's multiple levels to an industrial network, and as you move from just the sensors, maybe the little laser that scans the barcode, to the camera, the high-speed camera that looks for quality in your parts, all that information is wants to be collected, but also is stored somewhere. So the servers rely on that backbone, as well as any type of reporting software that would be on there.
I see. So more or less in the era of IIoT, communication is essential, gathering the data is essential, communicating it is essential. Without the industrial network, simply not possible. It's
Correct.
yes. Okay. It's the eyes and ears, and it's what moves the data. So moving on from that, I'd also like if you could explain how industrial control system networking differs from general industrial networking, and why that difference is especially crucial for plant floor operations. And maybe also while you're talking about that, you can also give us a little bit more information about the broader difference between enterprise and industrial networking as well.
Sure. ICS differs in the sense that general networking, or industrial networking, does not include certain handshakes or interlocks amongst processors and HMIs. So there's a relationship amongst those pieces of equipment, as well as safety protocols that are out there, and also just the sensitive ICS timing of devices. That communication that occurs, it works in milliseconds. So to break that down further in kind of the difference in a industrial and ICS environment versus an enterprise environment. Enterprise network, they value confidentiality kind of over the integrity or availability. The industrial networks, they require to always be available, always be there, always be reliable. And that integrity is a lot more important than just confidentiality. To use an example, if a operator has an issue with a part and walks over to that emergency stop button, you want that processor to understand that you stop right now. If somebody's reaching into a press and you hit stop and it takes its time to stop, that may not be a good situation. So there's a definitely an availability there, but also that sensitivity and that protocol being able to get from that HMI, that human interface, back to the processor to tell those machines to stop, or when to flip a bit. To kind of expand a little bit further into that, there's, like I said, there's handshakes. So that processor, that relies on the handshakes with the HMIs or the operator workstations. Sensitive program or PLCs and protocols is the timing. So if you have a processor that's telling a drive when to start up, or a drive when to rev up or rev down, if there's any type of congestion or issues on the network, that packet or that piece of information that's telling that drive or robot or machine to stop, if it has to send its message a few times, that's a delay. That could be a quality issue. There could be multiple issues down the road. So having a network that is very reliable and sensitive to those type of communications. And as I mentioned, kind of in my example, the safety it's always on my forefront whenever designing a network or going through the steps of helping somebody that is experiencing some sort of hiccups or delays. Is there safety on your plant floor? Because hitting that emergency stop and it doesn't stop, or you see a machine that's maybe starting to smoke, or a spark, it can always be hazardous.
Yeah, and I think on the difference between industrial and enterprise networks, someone once said to me that, if there's a few seconds delay when an email sends, or if a YouTube video has to buffer for a few extra seconds, it's no big problem. But
Right.
if some kind of motion control application, there's even a half-second delay, it could be disastrous and could be a huge issue. And so that's a quick way to sort of give a shorthand for the importance of low latency in that industrial environment. But so moving on to our next question for you, though, something else you mentioned in your article is you went over several technologies and protocols used in industrial control system, rather, plant floor networking. So if you could provide our viewers with some examples of how these are actually applied in real world industrial settings.
Sure. A few of them that come up are our first two kind of that I think of off the top of my head revolve to the kind of the network side and reliability of that network. So you have what's out there. It's called a DLR, which is a device level ring, or REP, which is it's a redundancy Ethernet protocol. And of that, DLR works in the sense that you can, it's they use the term daisy chain. It used to be used a lot. You connect one device in and then the next device out. DLR works in the sense of keeping that uptime. So it sends a token. So if you say you have 5 devices in a ring, and you're going around that ring clockwise, and for whatever instance, maybe you have a forklift driver or something cuts a cable or a bad cable, that token will understand that and then go the other direction, changing the communication route. So all the devices in this ring will continue to stay up, and that's where it differs from a daisy chain. Is you cut a daisy chain, the devices past that break are going to fall off. DLR works in the sense of being at the device level. It'll actually go the other way, and that way just the devices that are at that break are going to be lost. Rep works in the same way, just at a higher level for kind of that network backbone is where you would want to implement maybe a rep. Is you have multiple devices hanging off that, and if there was a fiber break one direction, it would then go to the other, keeping the rest of the network up and reliable. A more sensitive protocol that's used is PTP, which is precision timing protocol. That's used mainly by motion, drives, and safety. I like to think of it, if you think of like a drives and tooling, PTP is a protocol in which it's kind of a time synchronization. A lot of people in networking, you sync your computers up to a time clock on a server. This PTP uses they call a grandmaster, and it is the go-to for the timing of drives, safety, motion, and its particular importance is having it configured correctly. A lot of times these devices come default with it enabled. That allows it for kind of like it floats around. But properly configuring it and setting a grandmaster is important in that any device that is using that grandmaster or that primary device, it can be a PLC, it can be a switch, an industrial switch, that has PTP enabled. It looks at that for its reference points. So as a PLC instructs a drive to maybe ramp up, ramp down, or tooling to a change, or a robot and positioning its arm, it's using that reference point. If it's not configured correctly, say it's using a PLC A as its reference point, and then PLC A drops off the network, then it goes out and it looks for another device that has PTP enabled, but that other device may not have the same time as PLC A did. So it can cause the robot to malfunction. It can cause a retooling. Bottom line is it could cause a lot of downtime and broken equipment, bad quality. And then to reference safety again, it could be a safety measure if that laser or quality light curtain or something doesn't sense that somebody's across that and they're making a change, or reaching in to put bolts in a press, and then it suddenly loses its grandmaster and tries to find a new one, it's going to shift back to its starting point, and that could be somebody in the way.
I see. Very good. And now I think as we get a little bit closer to our conclusion, something else worth covering, and I think maybe you've touched indirectly on some of this, but maybe we can address it more directly, is improved productivity and reduced downtime as potential benefits that can be achieved through the proper use of industrial networking. So can you share with us any specific examples or case studies where industrial networking has directly impacted those things in a positive way?
Sure. Industrial networking, and as well as a reliable network. If you think of, and as an example, if an unmanaged switch is a typical go-to for kind of machine builders, that allows everything inside the panel to plug in and communicate amongst each other. If you take that unmanaged switch and you multiply it amongst, however many machines and process lines that are out there, you get a large network that is unmanaged. And by default, an unmanaged switch is going to send out a multicast. It's a protocol that says, it's a logical protocol that says, hey, this is who I am, so that way everybody knows who I am. If you multiply that in fold for every unmanaged switch and device that's out there, you have every device on the network talking to every device. And as I touched on before, you have those handshakes that occur between PLCs and HMIs and specific equipment. In that example, you have a unmanaged environment with everybody talking to everybody, and it becomes very congested and very cluttered very quickly. So that sensitive timing and congestion of traffic occurs, and you'll start having, network faults, machines randomly dropping off the network, etc. The fix to that is having a managed environment that's, one, reliable, it's redundant, and it's just manageable, just like it is in, the name of managed switch. You can manage that environment. You can help those devices, talk one-to-one, or, maybe they only need to talk to one or two HMIs. You bring one giant network of everybody talking together in the same room to a one-on-one conversation, much like we're having now. With that, you're going to get smaller logical networks and greatly improved communication speeds.
I see. Now, before we wrap up, I do just have one final question for you. So something you cover in your article, something else, is network segmentation, redundancy, and security measures as best practices. You talk about the ability of those practices, of course, to contribute to the stability and security of industrial networks, which is a topic we've also touched on several times throughout this discussion. But before we go, just share with the audience a little bit more about that, and if you could provide some examples of their implementation.
Sure. We'll kind of start with the network segmentation, as it'll kind of go into the redundancy, is the being able to identify and have that managed networks, and like I mentioned in the previous question, a smaller logical network. So you can segment physically. Typically it's kind of called air gapping. You've got, maybe your process lines are, separated by physical cabling. They can't see each other, they can't talk to each other. In other ways, logically, you can add, subnets and VLANs. One crucial way to do that is you can identify and categorize critical assets, drives, and other devices, but typically drives, they multicast. That's their default. They're going to talk to everybody. They want to. So you can logically segment those off to another VLAN. And if the routing is done, the architecture is done in your network correctly, they can still talk to the PLCs and drives they need to. They're just on a separate logical network. And that way their traffic stays kind of in their lane, if you think of a multiple lane highway. And then, you can set a higher priority on, PLCs or, critical lines. Maybe one process line is more important, or has a higher reliability than others. So that one gets a little bit more priority. And, adding security into that, maybe an operator on a different line, shouldn't have access to another process line. You can, by segmentation and computing, you can keep that user kind of only in his little workstation area. We see that more and more, coming from industrial computing, whether somebody's running like thin clients on the shop floor based off of maybe an RFID tag, or a login. That user only has specific rights to certain machines under his login, or at that operator workstation can only see 2 of the 3 lines. That's it's kind of becoming more crucial as we kind of move into security threats, and it's not just machines and data that's being taken. People are looking at, they'll look at those crucial machines or crucial lines on an operation floor, and maybe they'll hold those for ransom. And then adding redundancy into that helps with the security measures, as to it kind of falls back to that rep and DLR and such, is that if one is down, you're up continuously. You have that reliable network. You have the redundancy there. If you lose one, you've got another one that's going to pick up its place in real time.
I see.
You can kind of break down the redundancy into some different categories. You've got your data, which is your storage. That can be, historians collecting data in real time, as well as you could have processors that are acting as data concentrators, collecting those tags to push up to corporate for whatever type of portfolio that may be used. You've got system redundancy. That can be your computing. A lot of times you'll see that with HMIs that are being pushed out with some sort of thin client. You've got a primary and a backup, just so that way that thin client, whatever that screen is that user sees, it's always reliable. It's always there. You lose power, something gets cut, they're going to see just a tiny blip of a screen. Network, we've already talked about that redundancy. You can add layers to that by having Ethernet channels ran, where you can have more than just one cable that's running rep or DLR around the plant, but you can actually add a secondary cable that's running on a separate path even. So it doesn't take the same fiber route or copper route around the plant. It takes a different one, just so that way all your eggs are not in the same basket.
I see. So very good. Nick, I want to thank you for taking the time. There's been a tremendous amount of information that I think is going to be very helpful to our viewers and the rest of our audience. I do think we're going to go ahead and draw things down to a close here. To our viewers, if you like this material, I also encourage you to check out Nick's article in Control Engineering Magazine, which is linked below. And also, frankly, check out all the other great material in Control Engineering Magazine as well. We publish a lot, and there's a great deal more as well. So Nick, thank you one more time for sharing your expertise with us.
Thank you.
And to our audience, thank you for tuning in.